We're going to talk about Chapter 8, Land and Sea Effects. So this chapter, we're going to start with oceans and then air-sea interaction and talk about land. Climatic conditions are determined to first order by the nature of the underlying surface, whether it is land or ocean, and to second order by the presence of mountain ranges. The principal difference between land and sea lies in the penetration of solar radiation. On land, almost all the incoming energy is absorbed at the surface, whereas radiation penetrates several meters into the ocean. In addition, the water is in constant motion, mixing the absorbed energy. Consequently, there is almost no diurnal cycle in sea surface temperatures. In great contrast to the case of the land surface, mountain ranges affect weather and climate on local to global scales. Airflow is modified, clouds and precipitation are redistributed, and temperatures are changed both vertically and horizontally. We shall examine global climate through these lenses, starting with the word oceans. Globally, 71% of the Earth is covered by water. Hence, oceanic climates dominate the globe. The southern hemisphere is 81% water and the northern hemisphere 61%. Unlike the fresh water found in rivers, lakes, groundwater, and precipitation, the oceans are saline waters. Typical ocean salinities are between 32 and 37 parts per thousand. The surface layer is well mixed and warmer due to wave action. Below, this is a thermocline vertical temperature gradient to the deep waters that are cold. Abyssal temperatures average around 1.5 to 2 degrees Celsius. The ocean has a mean depth of about 4,000 meters. The Mariana Trench in the western Pacific reaches 11 kilometers. The factors that differentiate climate in different parts of the oceans are latitude, warm and cold currents, and global wind belts. The last of these was cheated in here. So here we examine ocean currents. The density of seawater at the surface is between 1,022 and 100,028 kilometers per square meters, compared with 1,000 kilometers per square meters for freshwater. At 0 degrees Celsius, it is 1,028 kilometers per square, while 26 degrees Celsius, it is 1,023 kilogram per square meters. In polar oceans, the density is mainly determined by salinity, while in tropical waters, the density is mainly affected by temperature. The distribution of temperature and salinity in the ocean surface waters is more or less zonal. The saltest waters are in the subtropics, where there is high evaporation. The tropical oceans are less salty due to river runoff, also as is also the case of the Arctic Ocean due to the northward flowing rivers in Asia and North America. Also, precipitation in the intertropical convergence zone (ITCZ) tends to lower equatorial salinity. The principal contributor to ocean salinity is sodium chloride, NaCl. The average ocean temperature is only 3.8 degrees Celsius, whereas the average ocean surface temperature is 16.1 degrees Celsius, and the average land surface temperature is 8.5 degrees Celsius. Water movement in the deep ocean is extremely slow, less than 0.1 meters per second, and so ocean circulations may take 1,000 to 3,000 years. Ocean temperature and salinity have been measured in all the world's oceans since 2007 by 3,200 free drift argon flows, small drifting robotic probes. Prior to their introduction, such data were mostly collected along ship tracks, where engine intake readings were taken. The floats move at a depth of around 2,000 meters, and every 9 days they profile to the surface and transmit the data via satellite. The record is not yet long enough to determine trends. So you can see the structure of the argon float. Very interesting. So argon float that measures temperature and salinity profile from 2,000 meters up to surface every 10 days. All over the world, till May 2011, there are 3,308 Arctic floats. So we can see that China have 46, Germany have 187, United Kingdom have 102, United States has the most, 1,756. It's very interesting. In the website that you can read more about argon float, the Argo is a global array of 3,800 free drifting profile floats that measures the temperature and salinity of the upper 2,000 meters of the ocean. So, ocean characteristics. A vertical thermal line circulation arises as a result of temperature and salinity contrasts that lead to density contrasts. In the ocean, cold and salty water is denser than warm and fresh water, so it tends to sink beneath the latter. These differences are the main driver of the conveyor belt that forms the global ocean circulation. The Gulf Stream North Atlantic current flows northeastward, cooling as it moves northward and eventually sinking in high latitudes, forming North Atlantic deep water. This dense water then drains into the ocean basin, and the bulk of it upwells the Southern Ocean. These components form part of the Atlantic Meridional overturning circulation, or global conveyor belt. Global conveyor belt measuring the strength of the AMOC is a challenge, especially in the North Atlantic, where the northern portions are fragmented by the land masses, and most of the sinking takes place in mesoscale eddies. Measurements at 26 degrees north show considerable interannual variability, with values of the AMOC falling from an average of 17 SV20 in winter 2009 to 2010 and 2010 to 2011, associated with a negative Arctic oscillation. SV for Sverdrup is equal to 1 million meters per second, square meters per second. The water, instead of going northward, turned eastward into the gyre. An analogous event occurred in the winters of 1968 to 1969 and 1969 to 1970. The reoccurrence in a second winter involves the re-emergence in early winter of temperature anomalies preserved in the seasonal thermocline. So we're going to reveal those ocean currents. So there are gyres in each of the ocean, the Pacific, Atlantic, and the Indian Ocean. Any large system of rotating ocean current, particularly those involved with large wind movements, is called a gyre. Current direction in general, currents in the northern hemisphere travels in clockwise direction in a gyre, while currents in southern hemisphere travels in anti-clockwise direction. Only exception is the current direction in Indian Ocean, which changes seasonal. The ocean current movement in North Atlantic gyre as well as North Pacific gyre is clockwise, while the gyres in the southern hemisphere are anti-clockwise. Current temperature in general, currents in the western part of every continent are cold. The exceptions are mentioned in the article on movements of the ocean water. Currents mentioned from the polar region are generally cold. Currents near to equator are generally warm. There is a counter-equatorial current which moves from west to east warm. The west wind drift moves from west to east cold. The Antarctic convergence is associated with this current. It is the region where the cold Atlantic waters meet the water of the Antarctic, creating a zone of upwelling, a zone of very high marine productivity. Gyres of ocean currents in each of the major oceans. The major loops are seen in Pacific Ocean, Atlantic Ocean, and Indian Ocean in both the hemispheres. Each of the currents follow more or less a definite pattern. But the currents in the Indian Ocean northern hemisphere change their flow direction between summer and winter. Currents of the Atlantic Ocean to the north and south of the equator. There are two eastward moving currents, the north and the south equatorial currents. Between these two, there is the counter-equatorial current which moves from west to east. Atlantic Ocean, southern hemisphere. The south equatorial current turns south and flows along the eastern coast of South America as Brazil current. At about 35 south latitude, due to the influence of westerlies and the rotation of the Earth, the current moves eastward. A cold current called the Falkland current, which allows along the southeastern coast of South America from south to north, joins with the current at this time. The Brazil current moves eastward and crosses the Atlantic Ocean as South Atlantic current. A part of the west wind drift of the Antarctica circumpolar current merges with the South Atlantic current while crossing the Atlantic. Near the Cape of Good Hope, the South Atlantic current is diverted northward as the cold Bacchanal current. Bacchanal current finally joins with the South Equatorial current and completes the circuit.